Hey everyone. I believe Dr. Iqbal may have told you that he is on out of for some conference, so I'll be taking the next two lectures as well, and for today's lecture. Okay. So for today's lecture, what we are going to discuss, that is actually the oxidation. In fabrication, one of the most important things is actually the oxidation. Anyone of you who has some experience of oxidation? Anything you know about oxidation? Nobody? Okay. So before the oxidation, I believe you should have discussed the diffusion process. Did you talk about the diffusion, or you have not discussed it yet? Diffusion? No? Okay. And the crystallographic orientations 10011, this thing you have discussed. Okay. Anyways, mostly in both this book as well, the book we are following as well. So I think so. Dr. Ball also follows. Diffusion is discussed after the oxidation, but according to me, diffusion should be discussed before the oxidation, because you will have to figure out what is the effect of diffusion in oxidation. Okay, but it doesn't matter. Okay, before we discuss the oxidation, when we talk about oxidation, we actually talk about thermally grown oxidation, that is thermal growth of silicon dioxide. Thermal growth of silicon dioxide. But you know, oxide layer silicon dioxide can also be deposited as well. But we are not going to discuss the deposition of oxidation, we are going to discuss the thermal growth of oxidation. So to be more precise, we will talk it as thermal growth of oxidation. But generally we call it as oxidation. Whenever I'm talking about oxidation, you will take it as thermal growth of oxidation. So what is the difference between growth and deposition?
Deposition, I'm just adding something.
Deposition means you are going to deposit something on some other surface. And growth means that something is already there, it's growing up. It's just like that a plant grows, and the second method is just that you take a plant and you deposit it. So today we are not going to discuss about the deposition, we are going to grow the silicon dioxide on a silicon surface. So it means the requirement in order to have the growth of silicon dioxide, what is the requirement? You should have the silicon substrate. So growth of oxidation cannot be done until and unless you have the silicon substrate. If you have a glass plate and you say I need to grow the oxide layer, you cannot grow the oxide layer, but you can deposit. On the glass slide you can deposit the oxide layer, but you cannot grow the oxide layer, because in growth means that oxygen and silicon, they react with each other and they form silicon dioxide. So that is what we call chemically they react together, and we say that oxide is being grown. So for thermal oxidation, for thermal growth of oxidation, we need a silicon substrate. On any other substrate, we cannot grow the oxide layer. This is very important. Keep in mind, if you don't have the silicon surface, you cannot grow, but you can deposit, of course. You will have to use some other method where you can deposit silicon dioxide layer. But if you say that you can grow, you cannot. And the first experiment that half of you have done that lab yesterday, actually, the first experiment is regarding thermal growth of oxidation. So you have the silicon wafer, we will put it inside the high temperature furnace. So that's why thermal growth. At high temperature, the oxygen comes in and it reacts with the silicon to grow the silicon dioxide. Okay, so this diagram is actually about the thermal growth Dale-Groves method. We'll discuss about that. First of all, what is the importance of oxide layer? What are the purposes? What are the benefits? What are the uses of silicon dioxide? To
insulate my whole substrate.
One purpose is isolation. Very good. Any other purpose? Yes, whatever comes in your mind. Sorry?
I mean, and a sacrificial layer to use.
As a sacrificial layer, that we call as masking. Okay, so it means masking means that if masking means to protect something from something else. This is called masking. So as a sacrificial layer, in technical terminology, we call it as masking. So means this part I don't want to grow. Let's suppose I don't want to grow. I don't want to deposit metal on this part. So what I'll do, that I'll have the oxidation layer over there. So after that, when I remove the oxide layer, so that part does not have the metal. So it means we have masked that part by using the oxide layer. So that's why, so one purpose is isolation, other purpose is masking, and the third purpose you may have heard in MOSFET is we use gate oxides. You may have heard about the gate oxide. So we use it as gate oxide as well. So these are the three basic and very important purposes of using oxide. Secondly, as we talked yesterday, that if you have the silicon at room temperature there is a native oxide layer that is not more than 30 to 40 angstroms, very thin layer, but there is a native oxide layer, and at the temperature which is used for this oxidation to grow up, because it's thermally grown, so at high temperature it grows up. So that temperature is actually more than 1000 degrees centigrade and less than 1710. So in that range, it's actually thermodynamically unstable. It's in amorphous state, in that you can say it is fused silica. It is in the form of fused silica. So that's why that at this temperature it's in fused silica, means it's in amorphous state. And why I call it as that, in this temperature range 1000 to 1700 or 1710 to be more precise. Why I say it is thermodynamically unstable? Because I say it's actually in amorphous state. It is called as fused silica. So it's trying to transform from the amorphous state towards its actual crystalline form, that is the quasi-crystalline form. So there is a thermodynamic force that is trying to convert from amorphous towards the crystalline form, that is named as devitrification. Let me write it down. Don't worry, we have not started discussing about this chart, so I'll talk about that. I'm just giving some basic information about so devitrification means that the amorphous oxide that is at high temperature, that is thermodynamically unstable oxide, tries to convert towards the crystalline form. Amorphous form tries to convert towards the crystalline form. Okay, now we talk about this thing. Now you have this idea that we should be, thermally grown oxidation means that a silicon surface at high temperature in the presence of oxygen. So that's why that is called thermal growth of oxidation. So this diagram is actually it's a model named as Deal-Groove's model that will find. He used some specific parameters to find out a formula to give us a model that can be used to figure out that what would be the thickness of oxide. So what it shows actually, this is the oxide thickness, this is the oxide thickness. What it shows actually, this is the silicon surface. Apart from this part, the right hand side is actually the silicon surface. Okay, from this point, the oxide, silicon dioxide started growing. So this is the growth of silicon dioxide, and this is actually the oxygen part, actually the gas. Okay, so you can say that actually from that part, oxygen is coming at high temperature. This is a silicon surface, so at the surface silicon dioxide is growing up. So this is what this diagram shows. So
what is C here?
The C is actually the concentration. C means concentration. I'm going to explain it. What Deal-Groove's method, he assumed that actually, just think about this, that you have the silicon wafer. I can rotate it clockwise by 90 degrees, so it would be this way: silicon surface, then silicon dioxide, and then oxygen gas. So that is the topmost part. F1 is actually the oxygen part. Okay. So what he thinks, he says that there are different three fluxes. F is actually showing a flux. What is a flux? Flux is actually, how do you define a flux? Number of atoms or molecules crossing per unit area in a unit time. So that is called as a flux. So he said that there are three fluxes that are involved in this process, in this complete process of thermal growth of oxidation. First of all, that is the oxygen. That is actually the oxidant. The oxidant is actually oxygen molecule here. The oxygen needs to be diffused from the source towards the surface. This is the first part, that is named as F1. And the second part, the same oxidant, that is oxygen here, or it may be the water molecule depending on, the oxidant is diffused through the silicon dioxide to reach the silicon surface where it can react. This is the second flux he named as F2. And the third flux is actually that at the silicon surface there is a chemical reaction between the oxygen and the silicon to make silicon dioxide. Okay, so these are the three fluxes that contribute towards the oxidation of silicon wafer, thermal oxidation. That means at high temperature, silicon and oxygen react together to form silicon dioxide. Any confusion up till here? There are three fluxes. First part is that the oxygen molecules need to come from the source, wherever the oxygen source is, towards the wafer surface. That is up to this point. And the second part is that it needs to be, that is, the oxidant needs to diffuse through that oxide layer to reach the silicon. And after that, it needs to get chemical reaction with the silicon, that is F3. So now you will get that idea that actually F1, I say...
I have a question. So there is already silicon dioxide layer.
Yes.
So, I mean, if we start from a pure silicon substrate, then there will be no layer of silicon dioxide layer.
If we start with plain silicon surface with no native oxide, so you say in that case F2 will not be there, right?
Yeah.
Because actually when the gas from the source reaches the wafer, it actually reaches the silicon surface because there is no oxide yet at the start point. Okay, so you are absolutely right actually. In that case, if this part does not come into play, what does that mean? That means that reaction would be faster. The thicker the layer is, the reaction will go slow, slow, slow and slow.
And there will be slope, downward slope.
Of course, slope down. That's why I say that I'll explain the factors as well. That first part you need to understand that first of all, the oxygen needs to reach, the oxygen molecules that need to reach the wafer. The second step, it needs to diffuse through, and that's why I'm talking about diffusion. It needs to diffuse through the oxide layer, whatever the thickness is. So it needs to diffuse through the oxide layer to reach the silicon, and in third step, it actually reacts with the silicon. Okay, so it means F1 is actually the gradient dependent, means that F1 is actually depending upon this. CG means concentration of gas, CS means concentration on the surface, and this Ci and Co means concentration at the inner surface and concentration at the outer surface, Co and Ci. So do you agree with me that F1 would be actually depending upon the gradient of the oxidant or gradient of the oxygen molecules? Gradient means, gradient means that higher the difference between the concentration at this level. Let's suppose here we have 2 molecules of oxygen, here we have 20 molecules of oxygen, so it will move from here to this side. And if we have, here we have 2 and here we have 2 millions, so it will move very fast towards that point. So that's why F1 would be depending upon what is the gradient of concentration at the source and at the surface. So no sooner that these molecules start diffusing in, more and more oxygen starts coming in. So this gradient is actually playing an important role for F1. F2, of course, because in F2 it needs to diffuse through oxide layer. So F2 is depending upon the diffusion coefficient, or I should say actually this is the diffusion equation. So this is the diffusion coefficient and this is the rate of change of the concentration. So F2 is actually depending upon the diffusion, F1 is depending upon the gradient, F2 depends upon diffusion. What do you think about F3? Anybody? F3 means in third step. What happens in third step? In third step, they chemically react with each other. So first step, oxygen reaches the wafer. Second step, it diffuses through to reach this silicon. Third step, they react with each other. Okay, so when they react with each other, it means that it depends upon, this Ks is actually the reaction rate constant. So Ks is actually the reaction rate constant. So F3 Ci. So whatever the concentration is at the inner surface multiplied by Ks.
How do we get Ks?
Oh, Ks, that's why these are constants, reaction rate constant. So reaction for every reaction rate constant is fixed. So greater the reaction rate constant, faster would be the reaction. So in third step, actually, the oxidation rate depends upon that how fast the reaction carries on. In second flux, the reaction rate actually depends upon how fast it diffuses through. Yes?
Shouldn't F2 be a function of distance? Concentration, it's a differential of distance, right?
Yes.
So it should be dou C by dou X.
You're talking about F2?
Yeah.
Yeah, that's why I say that it's diffusion. Diffusion is always depending upon the time and the distance.
So it should be both time and distance dependent.
Yes. That's why I say that this equation or this equation, both are actually, these three equations, they actually, these are the basics. So by using these three things, that F1 is depending upon Cg minus Cs, F2 is depending upon this thing, and F3 is depending upon this thing. After that, by using these three things, we come up with these final equations. So if you would have discussed diffusion, you won't worry about that. She is absolutely right, actually, that the distance, because that's why I was saying that thicker the layer, it will be more harder for the molecule to get through, because it's getting thicker and thicker. So when it's getting harder means when the oxide layer gets thicker, it means the rate goes below. It's more difficult for the oxygen molecules to reach the surface of the silicon. So in other words, you can say that it's actually we say it's the diffusion coefficient, that diffusion has become more difficult. Okay, so otherwise you can say that the distance, it needs to travel more distance, so it means it's more difficult for the molecules to get into. Okay, so after that, by using these three, I gave you the basic ideas, and after that there is a mathematical calculation of these three, that when we consider that at equilibrium means that F1 is equal to F2 is equal to F3.
No, there is a confusion, like in the previous slide.
Okay.
The function F2, I mean F2 depends on x, but you've written that it's dependent on t, I mean time. So will there be any component of X in your equation.
Oh,
what do you operate it?
sorry. It's, thank you. I think you indicated the same thing.
Yeah.
Oh, sorry. So it's actually the differential of concentration with respect to distance. Yes, sorry. So these three things, these three F1, F2 and F3, when you actually put F1 is equal to F2 is equal to F3 means you are assuming that the system is in equilibrium. In equilibrium means the amount of gas that reaches the surface, the same amount at that time, in that time, diffuses through the oxide layer, and the same amount in that time or the same number of molecules gets the chemical reaction with silicon. So we say that the system is in equilibrium, that nothing is changing. Whatever is coming in, the same amount is going through and the same amount is getting consumed. So F1 is equal to F2 is equal to F3 if we assume the system in equilibrium. You got my point? What do I mean by equilibrium? That the same number of molecules or atoms that move in the flux F1, that move from the source to reach the wafer surface, the same number of molecules actually diffuse through the oxide layer, and the same number of molecules actually react with the so actually I'm talking about F1, F2 and F3.
Yeah.
So by putting all three together, F1, when I say at equilibrium F1 is equal to F2 is equal to F3, by using that, these basic relationships, I come up with that equation.
I have a question. Like
Yes.
when my time goes to 0, I mean at the beginning maybe F1, F2, F3 might be equal, but when my time goes on, then I don't think. I mean,
Yes.
basically,
That's what I say, that system is not always at equilibrium. It's always limited. What is limiting, that actually we'll discuss this later on. That initially maybe we'll discuss it in the next slide, that what are the limiting factors in oxidation. But I said that just assuming the system in equilibrium, he's come up with this equation. But of course there would be some factors. The system would not be in equilibrium. It is not possible that whatever the amount we send in, all the same amount goes through the oxide layer. It's not possible. So, and whatever reaches the surface, everything is actually getting reacted with silicon. It's again not possible. Okay, so this is the equation that we come up with after a long mathematical solution, that is x square. This x is actually the oxide thickness. Keep in mind that this Dale Cruz method is actually to model the reaction rate of thermally oxide layer. The reaction rate means how fast the oxide layer actually develops. So the rate of the reaction. So we come up with the equation x square plus ax minus b into t plus tau, or the same thing, if it's on the other side, it would be equal to b into t plus tau. So this is the basic Dale Cruz equation that you need to keep in mind. This is very important, where you know that these a and b, they are constant actually, and similarly that tau, that is also a constant. So these a, b and tau, these have been actually from the same basic relationships, those three basic relationships. Then we manipulate it mathematically, we come up with this equation where a is equal to this thing, where b is equal to this, and tau is equal to this. So that tau is actually the initial oxide layer, the time that is needed, the time displacement needed to account for the initial oxide layer, tau. Because actually the tau, this tau, that actually tells you that what is the native oxide layer. If you start and initially it has some initial, we call it as the initial oxide layer or the native oxide layer. If it does not have the initial oxide layer, tau would be equal to 0. And if there is some, so let's suppose the initial oxide layer is there, and I say that in order to grow this oxide layer, that is the native oxide, it takes maybe 1 millisecond. So I'll have to put tau is equal to 1 millisecond. So I'll assume that 1 millisecond has already been passed. So tau is actually the time displacement needed to account for the initial oxide layer. And now you will find out, I'll let you know what is the significance of this A and B. Okay, actually, in this equation, what happens that if I say that the time, if I say that the time is much greater than tau. In other words, I am talking about the very thick oxide layer. Very thick oxide layer means X oxide is much larger. If I say T is much greater than tau means
Then we can ignore this.
X oxide is very large. If X oxide is very large, what we can ignore in this
We can
equation?
ignore tau. We can ignore tau.
We can ignore tau. At the same time, if X oxide is much larger, this square term would be there and it would be ignored. Because if the number is very large, its square would be much large. Okay, so I'm talking about the thick oxide layer. In this case, when we have put the wafer inside the thermal oxide, inside the furnace maybe for 10 hours, so there would be very thick oxide layer. In that case, I'll come up with X oxide square or we can follow that format. X oxide is equal to BT. X oxide square is equal to BT. So this is called as the parabolic growth. You can see it's a parabolic relation. So it means what I'm trying to let you guys know that this equation actually has a parabolic part as well as a linear part. So for very thick oxide layer, this relationship becomes parabolic, and for thin layers it would be linear. This is what I'm trying to show, that at very high temperature, at very high time, okay, this is for short, this is for long oxidation times. So this is what I'm trying to show, that for long oxidation times, Dale-Grove's relationship, that is, this equation is actually the Dale-Grove's equation, Dale-Grove's relationship, reduces to parabolic form. So you can see that this is a parabolic equation. X square is equal to BT. I'll talk about the second one as well. And similarly, if I'm talking about a thin layer, means T is less than or equal to tau, then if this is time is very small, means X oxide is very small. If X oxide is very small, in that case, what can be ignored? This X square can be ignored. So I'll be having from that relationship, if X oxide square is ignored, what I'll be having? AX is equal to
B tau.
B T plus tau. Because here we are not ignoring tau because it's equal to or less than.
Yeah.
Okay, so this is a parabolic relation, and if I ignore X oxide square, I will be left with X oxide is equal to B T plus tau. I'm moving A on the other side. So this is linear relationship or linear, and this is parabolic. So this is linear growth and this is parabolic growth. So it means that Dale-Grove's, now you can understand the next two slides. That for short oxidation times, now we're talking about this short oxidation. For short oxidation times, Dale-Grove relationship reduces to linear form. defined by B over A. This is actually the linear rate constant. So what you always be interested in? B and B over A. So this is your linear rate constant, B over A, and this is your parabolic rate constant. So B over A is actually the linear rate constant and B is the parabolic rate constant. So now you have understood that why it reduces to linear form. For short oxidation times, why Dale-Grove's equation reduces to the linear form? Because we ignore X oxide square. As compared to X oxide square being very small is ignored, so we get this. And B over A is actually the linear rate constant. And now the second line, definition of B over A can be further reduced by assumption that H is, what was H actually? If you remember that first slide, just this one, this H is the constant named as mass transfer constant. Ks is actually the rate constant, reaction rate constant, and this H is actually the mass transfer constant, mass transfer coefficient, and reaction rate coefficient Ks. Okay, now we were talking about this short time. Anybody who can define the second line, who could understand the second line from the discussion? The second line says definition of B over A, that is the linear rate constant, can be further reduced. Means we can also say that H is very, very large as compared to Ks.
That means my molecule at the what can I say?
Means that mass transfer coefficient is very high as compared to
all the molecules get reacted with the silicon.
Yes, now you get to the point that what are the limiting factor here? In this case, as you talked about initially, when there is no oxide, I am talking about the very thin layers. Very thin layer, you can say no oxide. Okay, at the start, it would be linearly increment. The greater the time, the greater the thickness. It would be in the linear portion. It would be in the linear region. Okay, in that case, I say that the mass transfer coefficient means that the gas can be transported from the source to the surface very fastly, but the limiting factor is the reaction rate constant. It cannot, because there is no resistance to the gas, so all the gas is reaching the surface. But the surface has limited number of silicon molecules, it cannot react with all the gas molecules at one time. So Ks is actually the limited. Ks means the reaction rate constant is limiting our oxidation rate. So this process would be called as reaction rate limited process. The third line also explains the same thing, that in this linear growth region, diffusion of species through the oxide plays very little role in determining the growth rate. Means that diffusion is not the process, is not the problem. It's not diffusion limited process. It's actually the reaction rate limited process, because diffusion is not becoming a hindrance for the molecules of oxygen to reach from source towards the wafer surface. It's actually the reaction rate that is decreasing the rate, or that is actually limiting our oxidation rate. That's why we say H is very, very greater than as compared to Ks. So this is the same thing that we are talking about. Okay, so we have completed the linear region. That is for thin oxide layers. We say this is the linear region, because in this region actually the oxidation rate is the linear growth oxide, and in this case the problem is with the reaction rate constant. Now what happens in case of long oxidation, means thick layers? Everything should be the opposite of that. In thick layer means that initially we were, if I draw the graph, it was linear and then it became parabolic. So we were talking about this part. This part has been discussed. Now we have entered this region, means thick layer. Now the oxide thickness has increased much high. So for the thick layer means for long oxidation times, Dale-Grove's equation becomes the parabolic growth. Parabolic this B is named as parabolic rate constant. B over A is the linear rate constant and B is the parabolic rate constant. Okay, and so I would like to mention one thing, that B over A is the linear rate constant. So because what happens that in exams you have B and A. In a table you are always given B and A and you are said that okay, find out what would be the thickness. So what we do, we know B is actually the parabolic rate constant. We take it B, the value from the table, and we don't think that A is not the linear rate constant. B over A is the linear rate constant. So you have B, you have A, you will have to divide those two values to get your linear rate constant. Don't use that A directly to find out your thickness. So A is not the linear rate constant, B over A is the linear rate constant, B is actually the parabolic rate constant. Okay, now the second line, you should be able to understand that in this parabolic growth, B is proportional to the diffusion coefficient in oxide. Thus, this is a diffusion controlled region. I told you that previously it was not diffusion controlled, it was reaction rate controlled region, because diffusion was not a problem. Now, because we have thick layer, so it means the problem is with the diffusing of those oxide molecules through the silicon dioxide. So the problem is with the diffusion. The diffusion is actually limiting our oxide rate. Oxidation rate is limited by the diffusion process, because whatever diffuses through, that would be reacted with silicon. It takes much time for the molecules to diffuse through the oxide layer. So that's why we say that when the thickness of the oxide becomes very thick, at that time the reaction rate would get slow due to the diffusion, because it's limited by the diffusion. So we say this is diffusion controlled region. It was reaction rate controlled region, and this is diffusion controlled region. Any question up to here? So now you got the answer of your question, that when it gets thick, there should be some problem. So now you come to know it is telling you, yes, there is a problem. In this region, due to the thick oxide layer, the diffusion does not permit all the gas molecules to diffuse through, because it will offer some resistance. It will be reluctant to letting all the gas molecules to diffuse through it. So that's why the very little of the gas molecules reach the surface, and whatever reaches, that is getting reacted, because there are more silicon molecules as compared to whatever is reaching when the thick oxide layer comes into play. Any confusion about the both these regions? That what is the difference between linear and parabolic?
So is there any critical point after which there will be no reaction between the silicon and oxide? Oxygen.
Yes, there are certain limitations that after which you can actually we'll talk about
certain thickness.
Yes, after that you cannot thick even. If I say that I want 1 mile thickness of oxide, so I cannot get it. So there are certain ways that because there are two types of oxidation actually. One is wet oxidation, and another one is dry oxidation. In wet oxidation has its own limitations, and dry oxidation has its own limitations. So in dry oxidation, I would say that you cannot get oxide layer even more than 1 micron. You cannot get there.
What's the value for which it stops being thin and starts becoming thick?
Sorry?
What's the value like after which it will start then you have to apply the thick oxide equation?
Okay, you're talking about that. What is the value of this point at which that linear region transfers towards the parabolic region? So just think about. We have discussed everything. You should know the answer.
T equals to tau. When T equals to tau.
No, tau is very small actually. I mean, tau is the native oxide. You can grow something. So in the next slide, maybe you will come to know about your answer. That is, it depends upon the condition. What is the temperature at which we are doing it? What is the orientation of the surface that we are doing it? So maybe that at 1000 degrees centigrade, it comes at maybe, if 1000 degrees centigrade, this point comes at 1 micron, it means that for 1500 degrees centigrade, it should come at 1.5 micron. So it means high temperature, so it makes the process a bit faster. So, and similarly, if we have 111 plane, we will discuss these things later on. So it depends on the process conditions. So that's why when you look at the graph, you will see something like this. So it means that it is for certain conditions, this is for certain condition, this is for certain condition. So whenever you need this B and B over A, you will ask about, okay, what is the temperature for this?
You already mentioned there is a range for these processes, like 700 to 1000. So can you go beyond that temperature, like you mentioned?
Oh, temperature, no. That's why I say that you cannot grow oxide.
Since you said 1500, so just for example.
Right? No, actually that was I was talking about the fused silica. You can grow, I mean, even at room temperature, the native oxide grows at room temperature, but that is very thin. You cannot, and what you can grow at 1000, you cannot grow at 200. At 200, whatever the time you take, you cannot grow that much thickness. So that's why I say it depends upon the process conditions. All this, what parameters we will see in the next slide. Okay, in order to find out these parameters B or A, it actually follows the Arrhenius relationship, that is B is equal to B naught E raised to the power minus EA over KT. T is actually the temperature, K Boltzmann constant, that value is fixed. EA is the activation energy, and B naught would also be given, it may be B naught would be given, that should be given at some specific temperature, and similarly EA activation energy should be given. So activation energy at different temperature and at different orientation, depending upon you are using 111 or 100, this activation energy would be different. So, but when you know EA, activation energy would be given in the table, B naught would be given to you. Just if you want to find out what is my reaction, what is my B or the reaction rate at specific temperature, you put that T value and you find out B. But usually we always get that from the table. But if you want to find out the value, from the given data, then this is the equation that you need to use: B naught E raised to minus EA over KT. You just put the value of the temperature. The rest of the parameters would be given to you. You should know about the activation energy for that specific condition. You should know about the B naught for that specific condition. I'm talking about the specific condition, means for that specific crystallographic, for this specific wet oxidation or dry oxidation. So depending upon that, you should be given the values. So by using the specific the given values, just put whatever the temperature you would like to. If you want to find out what would be the rate at 1000, put T is equal to 1000 degrees centigrade. If you would like to find out what is the rate at 1100, put T is equal to 1100. So by using that equation, you can find out those rates as well. So this is what I was talking about, the tables that at different temperatures you can see that A, B and B over A. Okay, in this case B over A is also given, but sometimes B over A would not be given. So if A or B is given, you can find out B over A. So you can see that higher the temperature, greater is the value of the rate constant. If you compare 920, B is equal to 0.203. And if you talk about 1200, B is equal to 0.720. So it means I'm just talking about the parabolic reaction rate constant. So that is much higher. As the temperature is high, the rate would be high. The reaction rate would be high. And one thing more, you should see from here that the first table is actually talking about the wet oxidation, and the lower table talks about the dry oxidation. So what do you see? The dry oxidation is faster or the wet oxidation is faster?
Wet oxidation faster.
Wet oxidation is much faster as compared to dry oxidation. Keep in mind, dry oxidation gives you better quality of oxide layer, but it's very sluggish, it's very slow. Wet oxidation gives you a faster reaction rate. You can grow thick layer of oxide in little time, but the quality of the oxide would not be that good that we can get in case of dry oxidation. So there's a trade-off. That at wet oxidation, thick layer can be grown, but not that good quality. At dry oxidation, you cannot grow thick layer, but the quality of the oxide would be really good. So what usually people do practically in labs or even in industries, if I need, let's suppose I need 2 micron or 1 micron thick layer of oxide. If I need 1 micron thick layer of oxide, I know that if I use dry oxidation, the quality would be good, but it will take more than 24 hours for 1 micron. So you cannot put inside the furnace for so much long time. So what they do actually, initially they grow, if I have 1000 nanometer means 1 micron, what they'll do, first 200 nanometer would be the dry oxidation, or first 100 nanometer would be the dry oxidation, just to have a better quality, to have a better isolation. Then fastly I do wet oxidation and grow up to 950, and the last 50 again the dry oxidation. So this is what they do. That this is the dry oxidation, then I go for wet oxidation, and at the top again a dry oxidation. So in this case you get a thick layer and you improve the quality of that oxide as well, depending on if I am using it for, let's suppose, isolation. So I would need that at this point there should be a better quality. Okay, so this thing you have realized from the tables, that higher the temperature, higher would be the rate. Secondly, wet oxidation would be faster as compared to dry oxidation. But the question is why? So far as why at high temperature the oxidation rate would be faster?
Because the concentration of molecule will be more, oxygen concentration.
I'm talking about temperature. Temperature has nothing to do with the concentration. You're right, concentration would also affect F1. If I don't let any oxygen get into, it means that first flux would be infected. I'm talking about only temperature.
Okay.
Why the high temperature lets you have the high reaction rate?
Oxygen molecule gets energized. So
Okay, if they are energized, just think about those 3 things. So what part, 3 steps, first step, second step and third, what part actually the more energetic or high temperature would be affecting into? F1, F2 or F3? The diffusion rate, okay. How about the reaction rate? Don't you know that at high temperature they react at fast? So the reaction rate is actually the major role. At high temperature, the reaction rate constant is always high. So at high temperature they react vigorously with each other, and because they are reacting faster, so it means that's why we are having that more or higher oxidation growth rate. So second question, that why the wet oxidation is faster than dry oxidation?
yeah, I said the molecule concentration is more in a wet oxidation rather than dry oxidation.
Why the molecule concentration is higher?
At F1.
Okay. At but okay, F1 is actually, it's absolutely the F1 is never going to be a limiting factor until and unless I want it. I mean the user, because whatever I want to, if I want that the oxygen gas supply should be getting into the furnace, so it means F1 would not be limiting factor. It would always be, we have we had learned this thing, it's always the diffusion control or the reaction rate control. It's never the transport control. So F1 is never the factor until unless I want it. F1, I can give as much oxygen as I can, but I cannot let all the oxygen to diffuse through. I cannot make anything possible to get all the oxygen getting reacted with silicon at one time. So that is the diffusion controlled or the reaction rate controlled. The transport is not a problem. So in wet oxidation, what is the reason? If you read the last two lines, you will get the answer. Sorry? Even silicon reacts the same way with oxygen as well. It reacts very fast with oxygen as well. Silicon reacts with oxygen to get silicon dioxide. So it's approximately the same. The reaction rate is approximately the same. So reaction rate may have caused the difference,
Diffusion rate,
but it's not the cause. Sorry?
diffusion rate will be different for different cases like wet oxidation and dry oxidation. As the line says, the oxygen and water diffusion through oxide much differently.
Yes.
So that's the reason, I guess.
That's the reason. That's why I said that read the last two lines, you will get the answer. That is, the water molecules, they diffuse through the oxide layer much faster as compared to the oxygen molecules. So that's why if we have a thick layer, oxygen molecules cannot diffuse through, because in case of thick oxide layer, it's always diffusion controlled process. Diffusion is the problem in case of thick oxide layer. So water molecules have got different diffusion as compared to oxygen molecules. So that's why water molecules can diffuse easily, and the solid solubility of water molecules is also high. So that's actually the problem is with the diffusion. So that's why wet oxidation is better in terms of growth rate as compared to dry oxidation. Okay, now we have discussed most of these growth rate factors because questions were coming from your side. So I was forced to explain those. That's why we have discussed most of these. That what are the factors why the oxygen, why the oxide growth rate would be limited by some factor. What are the factors? First thing, crystal orientation, as we have talked before, that it depends upon the crystal orientation. If we have got 1-1-1 plane, it would be having more growth rate, reaction rate as compared to 1-0-0 plane. Anybody who can answer that? Why 1-1-1 should be having higher reaction rate as compared to 1-0-0?
Silicon concentration.
Very good. That is actually the concentration of the molecules, the atoms. In 1-1-1 we have more atoms of silicon as compared to 1-0-0. So greater the number of atoms, greater the availability of the silicon atoms to get the reaction. So that's why the growth rate proportional to the number of silicon bonds per unit area available. That's why 1-1-0 is greater than 1-0-0. And I think you can now understand that why B over A was actually the linear
rate.
The linear rate constant, and that B is actually the parabolic rate constant. So parabolic rate constant is not being affected by the crystal orientation, but linear rate constant really strongly depends upon. Why is it so?
Because at that time the reaction rate is the limiting factor of the
Nice.
rate.
Because when I say the parabolic rate constant, so I am talking about the thick oxide layer. Okay, in thick oxide layer, the problem is with the diffusion. There is no problem whether it is 1-0-0, 1-1-1. We have enough molecules to get reaction rate. So it means that the orientation, crystal orientation, will comes into play when we have thin layer. When it is actually the reaction rate limited process, not the diffusion rate limited process. When the reaction rate limited process it is, then we need greater number of silicon molecules. So it means 1-1-1 is better than 1-0-0. Second factor is actually the dopant. When we have a dopant, whether it is boron or whether it is phosphorus or any other, actually the rate increases, the reaction rate increases. Why is it so? Because actually, do you know about the bridging and non-bridging oxygen in silicon dioxide? About the simply I would say, in simple words, I would say because they are actually the impurities. I mean, dopant is also an impurity. So due to impurity, the crystal structure it's not that strong as it was in case of no impurity. So when it's weak, so it lets the oxidant to get into. So the diffusion becomes easy. So that's in simple words. So to be more specific, you know that silicon, if this is a silicon, it is surrounded by, and similarly it goes on. So this oxygen that is being shared by two molecules of silicon dioxide, that is named as the bridging oxygen, because it bridges one molecule with the other. And if I talk about this oxygen, okay, so if I talk about this oxygen or if I talk about this oxygen, so there are, if it does not, it is not getting shared with some other silicon dioxide molecule. So it means that oxygen that is not being the bridge is named as non-bridging oxygen molecule. This is a non-bridging oxygen molecule, and this is a bridging oxygen molecule. So if in case of dopants, actually you will find there are more non-bridging oxygen molecules, because there will be some oxygen molecule that is not being, let's suppose we have boron. So it needs it has 3 electrons in this valence shell, so it needs only 3 oxygen atoms to get shared with it. So one oxygen atom would be there having no sharing with anything. Got my point? So that's why due to that impurity, there would be more non-bridging oxygen molecules. So the ratio of the non-bridging oxygen molecules towards the bridging oxygen molecules would be higher. In other words, I would say that my crystal has become weakened. So due to the weakness, or it is actually having some space to get the oxygen or any oxidant or the water molecule in case of wet oxidation to diffuse through it. So the same thing, due to the non-bridging oxygen molecules, the crystal becomes weak and it permits the oxidant to diffuse through it very easily. That's why the reaction goes up, because the diffusion becomes easy. So bottom line is, in this case, diffusion is easier due to the weak crystallographic system. Okay, pressure, this is also one of the factors. So if I increase the pressure, here where actually F1 comes into play, you're talking about F1. So if until unless I don't want, I said you, if I want to grow the oxide at low pressure, so I can do it. So I decrease the low pressure, but it will decrease the rate as well. And similarly, if I increase the pressure, it will increase the oxidation rate as well. So I believe that I don't need to explain why the pressure will increase it, because high pressure means it will forcefully push all the oxygen molecules to reach the wafer surface. So means F1 is faster. It will forcefully try to push it through the diffusion. So it means that it's trying to speed up the process. So higher the pressure, higher would be the reaction rate. And typically when you need thick oxide layer, in that case you go for the high pressure oxidation, that is, but in case of high pressure you get the thicker layer, you get in less time, means you have the high reaction rate, high growth rate, but the quality would not be that good. So it's always a trade-off. Mostly in oxidation, in the growth of oxidation, the greater the growth rate, the worse would be the quality of the oxide. Generally speaking, there may be some, but generally speaking, like pressure or temperature or anything else. So at high temperature, higher the rate, better would be the lower the rate, better would be the quality. Okay, So after pressure, there is an effect of chlorine. Now, if we introduce chlorine, this is also an impurity. So if we introduce the impurity inside our furnace, in that case, what do you think? The quality would be better or the worse?
Can you repeat the question?
Chlorine. What would be the effect of chlorine? Okay. So you are reading the slide. So chlorine would actually improve the quality of the oxide because it gets reacted with the metallic impurities. If we have got sodium ions, or if we have got potassium ions, or maybe of iron or anything, so it will get reacted with that, because after getting reaction it will become as a byproduct, and that is ventilated out of the furnace. So this chlorine is a very useful impurity that is introduced to improve the quality. And if we look at this table, you can see that there are different chlorine precursors or different sources that can be used or that have been used. But each one of those or some of those have their drawbacks. That's why we cannot use them. So I'll talk briefly. Chlorine can be used to provide chlorine, but the problem is that it's very corrosive, and due to the corrosion process, if we supply the chlorine gas, it actually takes those corrosive impurities with it towards the furnace. So that's why it's not used, because it will corrode the internal side of the pipelines or of the cylinder or anything. So chlorine as a gas is not that good source. So the problem is corrosion of delivery lines. You can see in the last column. Similarly, HCl has the same problem. And if we talk about dichloroethylene, TCE, that is it was when it was discovered that it can also be used to provide Cl2, that is the chlorine, and it does not corrode the surface. But later on we discovered that it's actually causing the cancer. So that is called as carcinogenic, means that it causes the cancer. So that's why it was banned. So we cannot use TCE. After that, TCA. TCA, that is actually 1,1,1-dichloroethane. It has been used in industry for more than 10 years. It was a very good source, but later on we came to know that it's actually having some problem with the ozone layer, so it's causing the global warming. So because this gas is causing the global warming, it was also not permitted to use anymore. So at last we used DCE and OC, and these were the good substitutes. We can use any one of these two. OC is even better than DCE. The reason is that in this case we don't have HCl as a byproduct. So why it is a better substitute? Because in this case when you react it, we get HCl as a byproduct, so we will have to take out and find chlorine and water molecules. So in this case water molecules does not come into play because we don't have the HCl as a byproduct. That makes it even better. But the last two can be used. Okay. One more thing, that Dale-Grove's method, I told you that if you draw it, it has some, initially it has linear region, after that it has parabolic region. This experiment we will do in the lab as well. The first experiment is the oxidation, and you will see initially it grows very fast, and later on it tries to get bent and tries to get constant at some value. Okay, so it gets into the parabolic region. So you have seen that I have not started from zero. I have started from here. Means for very thin layers, that is less than 30 nanometer or 300 angstroms. So it does not give you the right answers. I mean, if you use the Dale-Grove's model, it's very effective in use, but not for the very thin layers. At very thin layers, maybe less than 30 nanometer. If you use the Dale-Gibbs method, it will give you less thickness of the oxide, but experimentally you will find that you have a more thicker layer as compared to what Dale-Gibbs equation is giving you, because there are certain, it means the Dale-Gibbs method does not work well for less than 250 angstroms or 300 angstroms. So for the initial 300 angstroms, Dale-Gibbs method does not work well. The reason being, you can see there can be certain reasons that we have underestimating the oxygen solubility, or there may be more silicon available, and stress effect is also there, space charge effects. So there are certain reasons that actually Dale-Gibbs method does not include properly. But it's only for the first 300 angstroms. Later on, after 300 angstrom, this Dale-Gibbs equation gives you very reliable data. Okay, so now we talk about the silicon dioxide interface. As I told you initially, that today we are talking about the thermal growth of oxide layer. Oxide layer silicon dioxide can be deposited as well, but we are not talking about that today. We are talking about thermal growth. Thermal growth means that we need a silicon surface. So this is a silicon substrate. If we have the silicon substrate, then we can grow silicon dioxide in the presence of high temperature and oxygen, or high temperature and water molecules. If it is only oxygen, at high temperature we will say dry oxidation. If it is water molecules or steam, we will say it is actually the wet oxidation. What we will be doing experimentally inside the lab, that is dry oxidation. Okay, so silicon, and after that you have if this is silicon, and after that let's suppose I have 1 or 500 nanometer of silicon dioxide. So do you think it should be like this? I mean, the silicon surface should be still this thing, or it should change?
Amorphous.
No, I'm talking about just the surface layer. Means what I'm asking, if this is a silicon surface, so I want to deposit oxide, so it should still the silicon surface is the same at the same level. So it should be same level, or silicon surface actually go down?
It will go down.
It should go down. Why it should go down?
A portion of silicon will be
Consumed. Very nice. Because you know, in this case I am saying this thing again and again, that the silicon is getting reacted with this oxygen to get silicon dioxide. So if we have this much silicon, after we have 500 nanometer of silicon dioxide, how you can expect that the same amount of silicon is left? The silicon should also be getting consumed in that process. So some of the silicon should be consumed in the thermal oxidation process. So that's why it should not be like this. It should be like this actually. So I don't exactly remember, I think so that 54% and 44 and 56 I guess. So silicon is 44% approximately. I'm not very sure about these digits, you will come to know later on. So it means that if we have 1000 angstroms of oxide, out of this 444 of silicon and 566 I guess, or 36. Yes, it's 53.7, I remember. It's 53.7%. 53.7, and whatever the remaining, that is actually the silicon. it would be whatever is left of. So it's approximately 44 or 56, something like that. So some of the silicon is actually getting reacted with the oxide. So there is an interface. This is oxide. Now more and more oxygen is getting reacted. Some of the silicon is getting consumed and some of the oxygen is getting into play. So silicon surface also goes down, down and down, because a part of the silicon is getting reacted, and that is, it means every time, and this is the part where the diffusion process actually comes into play, because oxygen comes from here, it needs to diffuse through this oxygen. At this point it will get react and the oxygen thickness will increase, the oxide thickness. Okay, so after diffusing through here, the chemical reaction comes into play. So there is always an interface between silicon and silicon dioxide. At this point is actually called as silicon-silicon dioxide interface. So in case of at this interface, actually there would certain types of I would say defects. There are 4 types of defects that come into play. 4 types of defects. We call it as fixed oxide charge, mobile ionic charge, and interface trap charge and oxide trap charge. So these are the 4 types. Sorry. Okay. So yes, that diagram on the right hand side, you can see that where they actually exist first of all, and depending upon their position we actually name them. That interface trap charge, that is, we call it as QIT as well. So interface trap charge, so it is the first effect, interface trap charge. Where it actually exists, you can see it's at the interface of silicon dioxide and silicon. Its density, that how many these trap charges would be there, its density actually depends upon the temperature. That higher the temperature, lower would be the density. Means QIT is inversely proportional to the temperature. So it depends upon temperature, and secondly it also depends upon the orientation. Higher the orientation, greater would be QIT. So inversely proportional to temperature and directly proportional to the number of atoms in that particular orientation. And it's high for 111 as compared to 100. And similarly, the second one is fixed oxide. You can see that the fixed oxide is inside the oxide layer. These traps, they are also, but these fixed oxides, they are very close to their very close to the interface. It's mostly 40 or 30 angstroms above the interface. Fixed, yes, fixed, it's 30 angstroms, 30 or 40 from the silicon surface. So very close to the silicon surface. You can see here, this is fixed oxide. If this is a silicon surface, because this is a silicon surface, as I was telling you, this is a silicon surface, this is silicon dioxide, and that fixed oxide is always very close to the silicon surface, not more than 40 angstroms away from that. And this is named as QF. We call it as QF, that is fixed oxide charge. QF. This QF also depends upon the growth condition, that in case of wet oxidation, QF is always high, and in case of dry oxidation, QF is always lower, because said that these are actually the contaminations, or I would say defects. So that's why the dry oxidation is always better quality as compared to the wet oxidation. These are not very important, but you should at least know about that. What are the 4 types of the trap charges or the defects that comes into play at the interface of silicon and silicon dioxide. The third one is oxide trap charge and interface trap charge. I talked about interface trap charge. Yes, mobile ionic charge, they are actually above the silicon surface, as you can see there, and they are mobile as well, and they can have positive polarity or even negative polarity. And the last one is the oxide trap charge. And oxide trap charge is also depending on, let me see. Okay, it also depends on the temperature. That higher the temperature, less would be the defects. Means inversely proportional. So, as I told you that these are 4 types of defects that usually come at the interface of silicon, silicon dioxide. Not very important, but at least you should know about these defects as well. So we'll talk about the stress and why the stress is there, what are different 2 types of stress at the interface of silicon and silicon dioxide. But the time is up, so we'll be discussing it next time. Any question about whatever we discussed today? Okay, hope to see you in the next lecture. Thank you. Okay, you need some tweezer and pre-oxidized wafers. But why do you need pre-oxidized wafers?
Some research about nanopores. Joe will conduct a research and gonna help me.
Get some experience in
So, you're working with Dr. Iqbal's group, or
Yeah.
you come to the meeting?
Yep.
Oh, okay, I was missing in the meeting actually.
Okay.
Last meeting.
I thought you already know that.
No, I didn't know that. So it means you have the access to the reagent.
Yeah.
Okay, so in that case, actually, I know what Jobil is going to teach you. He'll be actually you'll be making the membranes.
Yeah.
That's why he is asking for the oxidized wafers, and after that you will be drilling some pore, but
With FFP and
F5B, but you won't be doing it at your own. I don't know, because I don't think so that Dr. Iqbal will let you train on the F5B, but you can make the oxidized, I mean the membranes. Yes. So you one oxidized wafer would be good for you.
actually 2. Since you're 2, show me the ones to get each.
Okay. Because I am left with only 4 wafers.
Oh.
Yeah. So, and I mean, the regular wafers we have many, but oxidized wafers I have only 4 of them. So you need to. I would say that for practice, it's good to start with 1, because it's 4-inch wafer.
Yeah, because each of us will be doing separate experiments. That's why.
But if you think that you are going to do it separately, I mean, if you're going to do it at your own, you won't be coming up with the right membranes. I know that.
Yeah.
Because you need to have some photolithography as well. You are trained on that photolithography equipment?
No.
The X-ray machine. Okay, you're not trained on that. And secondly, you have got the chemical training. Okay, so so far as I think, Joe Pillow will ask. He told you about the nanopores. He told this thing that you're going to put.
Yeah.
Okay, so it means I'm right actually. That what you will be doing, that you will be making the membranes on a wafer, and by using TMAH, and after making the membranes, you will be drilling pores in that.
Yeah.